Okay. Let's start with the new lecture. In this lecture, we're going to talk about some very applicable topics in signal processing, and they would definitely have so many applications in other areas. Maybe if we talk about the wavelets, then people interested in the digital image processing, they also would be probably triggered by this topic, and they will see that most of these topics that we're going to bring up in this lecture are somehow related to each other. And I'm going actually to talk about this relation and the basic theories necessary for them. Definitely what we are talking actually in this lecture is just a brief, and in order to be more aware of what's going on in the theory, you have to go to the books, to the articles related, and then everything would be more clear for you. So today's topic is about subband coding and multi-resolution analysis, and some of the subtopics coming under the umbrella of these two large topics are actually time frequency transform or joint time frequency transforms, like the Gabor and short time Fourier transform, and then the subject of filter banks and the wavelets. So let's start with this point that most of the signals that we were studying so far, they were temporal signals. It means that these signals had their variations over time. Irrespective of whether they are the discriminant signals or the random signals, they actually they had their variations over time, so they're called temporal signals. What we did so far, and we learned in the basic DSP theories, was to transfer this signal into another domain in such a way that we can see another feature of the signal, which is actually latent when we are looking at the signal in a time domain, and that was the frequency. So we elaborated the signal decomposition or analysis in the Fourier domain, aiming at getting the frequency components of the signal, and then based on the frequency components to extract some information across the signal. When we talk about these two domains, the time domain and the Fourier domain or the frequency domain, in the general sense, in the time domain, we're just having the signal with a very good resolution of time. So even if we are seeking for one sample data, we are able to get that sample of the data from that signal. So the signal purely in the time domain, it has the highest possible resolution in the time domain. And when we're talking about the frequency domain or the Fourier domain, we actually forget about the time resolution of the signal, and we are trying actually to get all the information of the signal, the entire signal, in the frequency domain with the highest possible resolution. But these are two ends. So these are the two limits of time and frequency. What if we need something more than that? What if we are actually interested in something, a kind of transform, in such a way that we can get some information of time and some information of the frequency? But we already know that there is no free lunch. So it means that it's possibly a kind of transform, if we can find it, it's possibly a kind of transform that we have to sacrifice one because of the other one. So if we are more interested in time, then we have to sacrifice some frequency components or some frequency resolution, and the other way around. In order to motivate this topic, let's have a look at the first signal in the upper curve. So that's the signal ST, and by looking at this signal, so this S of t seems to be a kind of, you know, just maybe piecewise stationary signal. Maybe piecewise stationary signal. But in general, it's non-stationary. So if you just take a look at the time interval between T1 and T2, what you can extract from the information of the signal is just like a single sinusoidal signal. So one frequency, probably one frequency. It means that if you just take this part of the signal, this time period, and then you transform it into the frequency domain, what you will get is just one delta at a certain frequency. And that frequency can be easily obtained using the inverse of the time period between two peaks, two consecutive peaks. Then if you put your window, your looking window, in the time interval between T2 and T3, you'll see that, well, it seems that the previous frequency is preserved. However, there is another frequency actually raised up. So the envelope of the signal is different. You know, it's not just constant like this. So it looks like that there is another frequency coming up. So probably if we take this part of the signal and then map it to the frequency domain, you will get two frequency components. One, because of these fluctuations here, smaller fluctuations, and the other one, or more details, and the other one because of this envelope. And the same way for any time period, any time window that you're actually taking a look at this, these periods, then you will find different frequencies coming up. So if you get the signal entirely in time, and then I'm asking you, for example, to map it to the frequency domain, then you will get all the frequency components of the signal at the same time. So, I mean, all the frequency of the signal, irrespective of the time, you will get it. The spectrum of the signal will be appeared in the Fourier domain. But if you're looking at localized, if you're looking localized in this time domain signal, then you will just see part of the frequency components and not all of them. For instance, if you see the T2 to T3 time period, you will never get the signal that might be as the frequency of this smoother frequency, the lower frequency that is actually on the envelope of the entire signal. You will never see that. Let's have a look at a more practical signal like the speech case. So this is a sample of the speech signal. And here, for example, it represents a part of the speech which is called the voiced region. So the voiced signal, like the vowels. And for the case of the vowels, if you take a look at a very short period of time, or the short window or frame, then it looks more like a stationary signal. So you see that this kind of pattern, for example, is repeated for several times. And there are some harmonics that you can just extract it out using some algorithms. If you go for the unvoiced regime, that you see that it's more like a noise, and there would be a lot more frequency components in the unvoiced part if you draw the spectrum. So that's a sample of a non-stationary signal, but if you just take a look at very small windows, then probably you'll have more stationary signal. So it's very important how you're localized in time, and somehow to make a trade-off between the time resolution and the frequency resolution. Okay, so it was clear from the examples that we saw that the Fourier transform is actually having the highest possible resolution in frequency, while the temporal signal has the highest possible resolution in time. And sometimes we need both of them. So we are actually looking for a kind of transform to have both at the same time. So let's have a look at these kind of signals. If you're just taking a signal, the Fourier of the signal, then with such kind of signals happen, like the left-hand side, which is a chirp signal, modulated actually with frequency. Then taking a Fourier transform of such kind of signal, actually Fourier fails in the sense that it will actually give you a lot of components. We know that one of the things that signal processing community is looking for is to find a kind of transform which is actually giving us a less number of the coefficients for that transform. So the more sparse the transform is, the more interested that transform is. So we are actually looking for the kind of transform to be more sparse in the domain. We saw, for example, this sinusoidal signal is, we are actually able to represent this kind of signal in Fourier domain just with one single delta and one coefficient. For many signals, it would be possible to represent it in the Fourier domain with just a very few number of the samples and the coefficients. But for such kind of signal, even though it looks actually very simple, but going to the Fourier domain, we will get a lot of samples. We'll get a lot of actually coefficients for the Fourier. Or if you have a kind of signal like the right-hand side, which is a spiky signal, then because of this spike that we see here, for example, localizing time, then we will get, for sure in the Fourier domain, we will get a lot of coefficients activated just because of this spike. While we see that this kind of signal is so simple, and it should be another way to see this signal much simpler with a less amount of coefficients or more sparse representation. In order to be able to develop an idea about that, we have to go back to a theory in physics which is actually developed by Heisenberg, and it's called the Heisenberg uncertainty principle. So what Heisenberg says is that we're not actually able to have an extremely localized view of time and frequency at the same time. So there is a lower bound for the resolution that we can have in both time and frequency. That would not be possible to have extreme accuracy for both time and frequency simultaneously. We have to sacrifice one because of the other one in any kind of transform that we are actually looking for. So the theory comes actually like this. So assuming that the signal is energy signal, then the absolute value of the signal square is actually representing the energy. And if we assume that the entire signal's energy is E of x, it means that this absolute value square over E of x is actually normalized, the normalized version. And it means that this is actually somehow representing a kind of probability. And then we are looking for time and frequency and how the signal can be scattered over the time and frequency at the same time. So it's a kind of two-dimensional scattering So if you take the time, actually the average for the time, the mean of the time localization is actually taking the average over the time as a random variable, and the probability of that localization of the time, which is actually this energy. So the energy of the signal over the entire energy of the signal, which can be represented as kind of probability. So T times the probability of time. And this integration is actually nothing but an average. The same thing goes for the frequency. Because of the Parseval theorem, we saw that the energy of the signal and frequency and time are the same. And this is actually, this absolute square is actually the energy of the signal in the frequency domain. So this ratio between the energy of the signal and the entire energy of the signal is actually like a probability, and taking the integration of f times the probability of f over the entire frequency range is nothing but the average of the frequency that we can have. And for the variances, we have to just subtract out the mean for the time and the frequency, and the same equations we use. So we have the mean and the frequency, or how the scattering of the signal would be around the mean for the time and for the frequency. Heisenberg could actually prove that the variation over time times the variation over the frequency, the point of localization actually, the variation over time times the frequency variation is actually following this kind of inequality. And the lower bound of this inequality is something like this, 1 over 4p. And this lower bound will be actually respected if we are using a Gaussian window. So if you're using a Gaussian window, then we would be able to hit the lower bound of this inequality. And what other result we can get from this inequality is that, so this variation over time and variation over frequency, taking it as a constant, for example, if you are hitting the minimum, if you are actually hitting the lower bound, when it's constant, it means that you cannot have the delta t, for example, the variation over time, to be around 0, because if you do that, then delta f would be around infinity. So you will lose one of them, the delta t or delta f, or you should have some compromise between the amount of variation that you want to have over the time or over the frequency. That was the motivation that for actually the joint time frequency transforms, and later on for the wavelets. So wavelets, even though the first wavelet was actually developed by Alfred Haar in around 1910, I think, but they were actually put into the practice around the 1990, in that decade, almost end of the millennium, the last millennium. So joint time frequency actually was earlier than this time, maybe around 60 or 70. So the idea of joint time frequency is not something very new. We actually, if you know something about the musics, then what you see in the music notes is actually very much similar to the idea of the joint time frequency. So in every music note, you see, for example, here is an octave of a kind of instrument, musical instrument, which is played, maybe a piano. Then you have these windows over the time, which actually somehow determines the rhythm for that music. And then you have these signs for the frequency that should be played at certain time. But you have to, so we can say that this is kind of time window, the rhythm that we have, the musician should actually take care about that. And then all these frequencies should be played actually within this time window. So looking at this graph, the musical note graph, we get the intuition that it's just like to have a two-dimensional representation over time and frequency with some divisions or the windows in the time and over the frequency. So the idea of all the transforms that we'll see in the joint time frequency and the wavelets is that this time and frequency rectangle actually, which comes from the Heisenberg uncertainty, this can be divided, but the way that we go for division of this space, this area, is actually the idea of many of these methods. So we'll see later that if these smaller windows, these quantized windows, if they are constant for all the frequencies and all the time, then it's nothing but the short time Fourier transform. And if it's dynamically changing based on the frequency and the importance of the lower frequencies with respect to the higher ones, then we are going actually to the filter banks or the wavelets. Okay. So having this signal like this, we know that if you remember what we said about the Fourier transform, so in Fourier transform, what we mentioned was that every signal was, maybe it's better to write it down now. So let me first stop this one. Okay. So in the Fourier representation of the signal, we saw that if we have the signal x of t, which we can represent it, for example, as the coefficients like xk or x to the power of j omega t, j omega actually, e. So that was the representation of the Fourier, the STFT. So we saw that these are the eigenfunctions or the basis for the Fourier domain. And the signal x of t so can be synthesized based on these basis functions. If you look at this form of the integral, it's actually telling me that that's a kind of, it's a kind of inner product, or how much from every of these basis functions are actually used. These basis functions are used actually to somehow construct the signal x of t. Now the point is that for the joint time frequencies, we are actually looking for the same thing. So we need to find basis functions such that every signal in the time domain be constructed based on these basis functions. Now if you take a look at here, so if you take a look, can you see it? Okay, let me make it a bit bigger maybe. So if you take a look at the signal S of t, if you take a look at the signal S of t, then you will see that this signal, it can be actually represented based on the basis functions like t of s, like the h actually, with respect to two indexes m and n, which one represents the time and the other one represents the frequency resolution. And the signal, inner product between the signal and the basis, gives me the coefficients which the signal can be instructed based on that. The same way that we had for the simple Fourier domain. So in the simple Fourier domain, we can construct the signal. So this is actually the same way that we have here for the S and H as the basis function. So we have the same thing here. So it's like just like to say that x and these basis functions, which are a to the power of j omega. So the same type of equations could be written in order to get the signal, the synthesis of the signal based on these basis functions, or the eigenfunctions actually. So in every domain, we are looking for some eigenfunctions or the basis functions in such a way that the signal could be spanned based on those basis functions completely. The difference between the joint time frequency and the Fourier domain is that now we have bases in both time and frequency at the same time, because we are looking for a kind of transform, so it should have this property to actually represent both time and frequency at the same time. And this H is actually the one that plays this role. M and N are actually the indexes based on the time and the frequency. Now the point is that this localization over the time and frequency gives us the area like this. If the way that we are localizing time and frequency are completely identical, then this area would be, if the time and the frequency localization are completely identical, then this area would be circle. If you give some preference over the time or the frequency, then this area will be elliptic, and that depends that elliptic to be horizontal or the vertical, depending on how much you want to be localized in time or the frequency. Okay? So the t values are actually the coefficients that if you use it over this basis, then you can actually construct the signal S. But here you have two sigma values. You have two times integration, one for the integration over the time and the other one for the integration over the frequency. But how practically it's implemented, it's actually this way. So you have the signal. Here is the signal, ST, for example. What we do is we take a window of that signal. And that window, we're not talking about the type of the window yet. But based on the type of the window, then the different types of joint time frequency transforms that can come up. But we can make a window over the time. We put the window on the signal, multiply with the signal. So far we have the signal in the time domain. Then whatever we got, we actually map it into frequency domain. then we have both localization over time and over the frequency. So the more localized in time, then less resolution in the frequency we will get. And if you make this window for the entire signal, for the time period of the entire signal, so you're actually losing the localization over the time. If you make it the limit, in the limit, if you put it this window, I mean the variance of this window to make it as the length of the signal, then the result of that would be the highest resolution in the frequency. So you will get all the frequency components, and that's exactly what Fourier analysis does. So that's the trade-off between the time and the frequency. Based on this, there are different transform-based methods that are developed. So one of them is windowed Fourier transform, or short-time Fourier transform, and is abbreviated by STFT. Short-time Fourier transform, or windowed Fourier transform, is actually the one that uses the same theory. So the signal x of n is actually created based on these basis functions or eigenfunctions psi of k, and the coefficients are nothing but the amount of, or the similarity between the signal and these basis functions. So the amount of similarity between the signal and any of these basis functions, phi k, psi k, k changing from 1 to any, gives us the coefficients for that. So the short-time Fourier transform, as we explained in this slide, is actually making a window over the time, multiplies that window with the signal in time, and then after multiplication, it actually goes to the Fourier domain. So you see that ft is multiplied by this window wt, and then the Fourier domain transform, which is actually this integration with this eigenfunctions in the Fourier domain. But you see that this window is actually, we are able to translate this window over time, to shift it over the time by changing t. That's actually what it does. And here it means that STFT, based on the previous definition that we had here, STFT is actually trying to find, so the coefficients of STFT are nothing but the correlation between the signal in time and basis function, which this basis function is nothing but the window, any window that we want to select, times this eigenfunction, the pure eigenfunctions of the Fourier domain. So we have a basis functions which is more complicated than the one we had in the Fourier domain. Then the signal times this one, the inner product of that will give me the STFT coefficients. And again, whatever we get in STFT are in complex domain. They're not real. These STFT values squared are called the spectrogram. So whatever we see in the spectrogram command in MATLAB is actually the magnitude square of the short-time Fourier transform version of the signal. So it means that here you have time which has already been divided into slices. We chop the signal in time, then we multiply that by a window, and then take the Fourier transform of that, and this is how it's represented. So it's a three-dimensional signal: time, frequency, and the intensity, which actually represents this magnitude square. So here, the darker the values, it means that the magnitude square is more. So that's called the windowed Fourier transform, or short-time Fourier transform, STFT. Now, the point is that based on the Heisenberg theory, we saw that there is a lower limit for this resolution. And that lower limit would be hit by the Gaussian kernel if we use a Gaussian window or the Gaussian kernel. So Gabor transform is the short time Fourier transform which uses the Gaussian window, exponential window, Gaussian window. That's all. So this basis function actually changes to this one in time domain or this one in the frequency domain. And then if you apply this, so that's the kernel. For the Gabor, the kernel would be like this. For the short time Fourier transform, it was like this. If you change the W here, the window, to be this G function here, which is represented like this, in exponential form, which is actually the Gaussian kernel, then you'll have the basis function for the Gabor transform, which actually gives us the best possible resolution over the time and frequency at the same time. So that was the definition for the Gabor and STFT. In this slide, we're actually studying some drawbacks of STFT and Gabor that actually motivates us to go through some other types of representation of the signal. So we see that we take the signal in real domain, so it's in a Hilbert space in the real domain, and then we go to we actually add another dimension to the signal, and this extra dimension is actually meaning that we have a redundancy. We have this redundancy. So we are actually losing the efficiency of representation in some sense, to the cost of getting some more information out of the signal. Another point is that we are actually having some localization over the time and for the frequency. But the point is that whatever we get as the time or the frequency window, that will be constantly remain for the entire signal. So it doesn't matter whether the signal has more, more information in the higher frequencies or the lower frequencies, we're getting the same strategy for the entire spectrum. Maybe it's not an efficient way of going through the representations. There are some different other joint time frequency transforms. I'm actually skipping this, but you can go through the literature to find out the Wignerville and pseudo-Wignerville and many other methods. So for the Wignerville, as just an example, you see that, well, the frequency eigenfunction is still the Fourier one, but for the case of the time one, we are not actually doing the windowing. We are actually taking the signal in time itself, and we're moving the signal over itself. So by shifting, you see that this is a signal and the conjugate version of the signal, which is actually the signal, and we're actually moving the signal to the left and right and passing through itself instead of doing the windowing. So what it does is actually something like that, and also the Fourier basis, which is actually the same thing that we had already. So again, we're coming back to this area, this actually Heisenberg uncertainty principle. So the time frequency area. So we saw that in joint time frequency methods, we had a constant division of this area. And that would not be an efficient way to do that, because many of the signals, they have their information in some part of the frequency. So most of the signals in the lower band of the frequency, they contain more information than the higher bands. And mostly the higher bands belong to the noise. It's not good to have, the localization preserved constantly for lower and the higher frequencies, like the one we had in the STFT. So there are some other transforms that they actually propose to have a different way or a dynamic way of representation For example, if we have the lower frequencies, maybe it's better to lose the time. The time resolution is actually lost. But by increasing over the frequency range, we see that we are more localizing time and losing the frequency information. So here we see that the window for the frequency, the localization over the frequency, here is so tight, but here is so loose. So there are 3 different ways to represent a signal in more than one domain, which is time. One was the STFT or Gabor, which actually is the constant tiling. This is called tiling of the time frequency area. And we actually talked about that. Then we have filter banks. Filter banks try to have a desired tiling in the frequency. So we can have, if you have the frequency spectrum from 0 to 2 pi, then we have different types of filter banks that can divide this spectrum into uniform divisions or non-uniform versions based on our desire. And we have wavelets, which are actually non-uniform tiling, something like this. Also, there is a big difference between wavelets and filter banks. Joint time frequency transforms and filter banks, they are actually talking about time and frequency. But wavelets, they're talking about time and another quantity, which is actually scaling. And scaling is somehow indirectly dependent on the frequency. So it's not directly talking about the frequency. So here in wavelets, there's a big difference between wavelets and filter banks, even though they seem, very much identical. But wavelets are not talking about frequencies. They're talking about signal in time and scale. Let's go through that. So the second topic was about filter banks. Still we are in time and frequency, but the way we're going to that is a bit different from the joint time frequency methods. Filter banks, so any questions so far? Anything about the joint time frequency, STFT, Gabor? Everything was clear? Okay. So there are different design approaches for the designing of the filter banks, and also some implementation methods which can somehow make the practical usage of the filter banks more efficient. So we have critically decimated filter banks or perfect reconstruction filter banks and many other different methods. And for practical implementations, we have some efficient ways like the modulation or the half-band filter bank design or the polyphase filter bank design. We already talked about the polyphase when we were talking about the sampling rates and variation of the sampling rates. But in the coming slides, we're actually talking more in details and how it can be implemented. As an example for the filter banks in the literature, you might see something like the quadrature mirror filter bank, QMF, or uniform DFT filter banks, cosine transform filter banks, and conjugate quadratic filter banks, and so on. But these are among the most prevalent filter banks used in these in the practical cases. The idea of filter bank is, instead of going through the signal, the entire signal in time, we can actually have the signal divided over the spectrum, and then we can manage every spectrum band individually. So let me have a simple idea to bring up as so we have a signal x of n, And we are actually, in general, in any telecommunication task or any kind of task, we have this signal passing through a kind of system like H, and then we do a kind of process, and finally we want to get back the signal in time, so we do the reverse process in order to get something like y of n. So the point is that this part of the process should be completely equivalent to this part of the process, in such a way that if there is no process doing here, so if this part of the process is actually nothing, so we are just analyzing the signal or filtering the signal here and then doing the reverse process here, we should be able to get the same signal here exactly, or at least a very good approximation of the signal here as x of n. So doing the subband processing is something that we are actually seeking, motivated by the idea of, by this actually idea that maybe it's much better to have the signal x of n divided into the different bands, different filters for different parts of the spectrum, and then if we want to do any process, we do on the subbands, and then we do the reverse process to get it back. So here, y of n. But the first questions that come to the mind is that, okay, why not just taking one filter and doing in the entire band without going to the subbands? Is somehow showing, is somehow, you know, implicating a kind of, you know, extra effort and extra computation. So why should we go through such kind of, you know, extra computation if it's not necessary? So let's investigate if we can actually have everything just by using the idea of simple filtering and then doing the reverse process. So this is actually nothing but the inverse filtering. This is called the inverse filtering. Inverse filtering. Now the point is that, okay, if we assume as an example, and with this example we can show that there is a problem with this idea, then it means that we have to find something, a better way of doing that. So this example I'm actually giving from Professor Radke from Rensselaer University. So using H, for example, to be 2/3 and 1/3, which is actually in Fourier domain, it's actually 2/3 plus 1/3 to the power of minus j omega. It's an FIR filter. So if H is an FIR filter, then simply, if we know H, then we know that G should be H inverse. So it would be 1/2/3 plus the rest. But it's very easy to show that this is an IIR filter. So even though in FIR filter we had just 2 taps, so the FIR filter only has 2 values, so 2/3 and 1/3. But now here the IIR filter means that we have unlimited number of the taps. So it goes to infinity. Another problem is that if, for example, let me clean, so that was one of the examples, but let me clean this part to give another example, or maybe you can clean it up completely and then I can write it down again. So assuming that we have h of n, a low pass filter with the coefficients of 1/2 and 1/2, and assuming that we have a signal x of n as something like this. So just by looking at the signal, we see that the signal has the maximum frequency possible. So alternates between 1 and -1 for every sample, and it means that it has the frequency, the highest frequency, which is pi. So why is not writing? So the frequency of the signal would be pi. So now if you pass it through this low pass filter, the output would be always 0. So we give x of n to h of n but then here everything is 0. How can we do the reverse process? So it's not possible. Using a single filter, we would not be able to get what we actually need. That's why we normally go to the subband processing. So now let's go to the subband processing, particularly the filter bank. So there are different ways to divide the spectrum actually, but the general structure of every subband processing or every filter bank would look like this. So we have the signal x of n. We divide the signal, we actually pass the signal over the division in the frequency. So every filter is actually occupying part of the frequency spectrum. So H0, H1 until, for example, if we have M branches, then we have M filters. And each filter takes part of the spectrum. So H0 to HM-1. We pass the signal through each of these filters. But we know that when we pass, for example, the signal to for example, this one is the low pass filter, then this is the band pass filter just coming afterwards, like this, if this is the spectrum. Then you have the low pass filter, then the band pass filters, and so on. Oh, sorry. So here, low pass filter and the band pass filters and the high pass filter here, which is actually close to the higher possible frequencies. Then we see that, okay, so we can actually do the downsampling here because the only part of the signal which is actually passed through this filter are the lower bands, and most of the others are actually filtered out. So we can have we have the the redundancy in the information. We have M bands, so we can do the decimation over each band, M times for each of these branches. And then in the reverse process, if we do nothing in between, then we have to do the same thing just in the reverse order. We do the upsampling and a filtering, and then superposition of them should give me an approximation of the signal we had here as an input to the entire analysis part. So this first part is called the analysis filter bank, and this mirrored version of that is actually called the synthesis filter bank.
Could you please explain why you downsample it after the filter?
Let me show that in the example. Maybe it's much simpler to see it in an example. So that's called the analysis and the synthesis filter bank, and the entire structure is called the filter bank. The way that we go through the spectrum, we can have uniform divisions or we can have non-uniform divisions, logarithmic divisions or non-uniform divisions, and so on. For example, in MFCC features, for the speech features, MFCC features are extracted based on the MEL filter bank, which is logarithmic version of the filter bank. So the spectrum is actually logarithmically divided, and then the signal is passed through that. As an example of these filters. So H0, H1 onto HM minus 1, and these are actually the cutoff frequencies. Let's see a simple example, and then we can go through the more specific example that you can understand exactly the divisions, decimations, and interpolation factors. So if we have just two branches, x of n as a signal is passed through two filters, one for the lower band and one for the higher band, downsampled, and then the reverse order is taken, so upsampled and so on. So one of the points is that, just to give you an answer, when you have the signal, for example, in time domain, to have the length n, then when you pass it through the filters, low pass filter and high pass filter, then again the signal that you will get in the outputs are n and n. So you have n taps for the lower pass signal and n taps for the higher pass signal. So you are actually getting the redundancy. You're having a redundancy. You have a signal n, length n, but again you are getting 2 times n. And half of each of these filtered versions of the signal, half of the information is actually not necessary. That's why you do the downsampling with the range of 2. The rate of downsampling should be 2 if you are 2 branches. Then you have n half for the lower band and n half for the higher band, but entirely again you have n samples. And you do the reverse order. But the point is that these filters actually are not completely this inverse. So these H0 and G0, H1 and G1, how they should be designed. What are the conditions for designing these filters? That's the story of the filter bank. Yes?
Why should you do downsample before upsample? Isn't it better to do upsample after downsample?
In general, if you do the upsampling and then the downsampling, nothing happens to the signal. So there is no danger happening for the signal. But the point is that in order to analyze the signal, you need to have downsampling coming first and then this upsampling.
You might lose data, right?
Because you're actually doing the sub-band coding. So you have sub-bands. You pass a signal with length n to any of these sub-bands. You have the redundancy. If you do the upsampling, you're increasing the redundancy. So we want to get rid of the redundancy. That's why we have to do the downsampling. But the point is that when you do the downsampling, then these two filters, then it's important. You have the downsampler first and then the upsampler. So it's a decimation filter, and here you have a interpolation. Coming this way, decimation first. So we have to take care how we design this. The story of the filter bank is actually how to design this in order to get the best efficient filter bank that we can have. Now, here we're talking about that efficient extraction, actually, the derivation of the filter banks. for a 2-channel case. So the best thing that we can get out of this filter bank is that we have something in the output without any kind of distortion with respect to the input, except for just a linear shift or linear phase shift, which is acceptable. So if we have just some samples delayed, so if x hat of n is exactly the same as x of n with just some samples delayed, that's the best thing that we can have. We know that no system can give me an instantaneous output when I give the input. So if I give the x of n, there is no real system that you can design in such a way that you can get exactly x of n in the output at the same time. So for the same n, if you do any process, no process here. So there would be some samples delayed. If you get some samples delayed in the output with respect to the input, that's the best thing that you could get. Okay? And some samples delay in the z domain could be simply represented by this. Z to the power of minus d. D samples delayed. So that's what we desire to have. To have the output in the z domain look like this with respect to the input. Just some delays in the samples. That's the best thing that we can have. And if you get to this, if you can satisfy this condition, then the type of the filter bank you design is called perfect reconstruction. Perfect reconstruction. So perfect reconstruction filter bank is the one which can satisfy this condition. Yes?
What is z power minus d?
It's representing the delay.
Delay.
Yes, in Z domain, when you are representing a delay, Z to the power of minus something. So if you have K samples delay, Z to the power of minus K,
Okay.
and here it means the minus D is D samples delay. Now extracting this information would be so easy. Maybe you can go through these derivations here, or in a simpler case, I can just write it down again. I'm so happy with this, writing that frequently. So let me see if I can. Okay. So, assuming that we have this x of n pass through h0, and then we have here g0. So we saw that we have to pass x of n through two different channels, and then we have to sum up all the things here. That's why we call this y0, and this is x of n here. Actually we have x of n. So for this simple branch, then we can generalize it to the other branches. For this simple branch, it's simply easy to say that, well, we have here, so we have down sample and up sample also here in the line. So now if we're just looking for the first one, y0, we're talking in Z domain, so the y0 would be 1/2 of this g0, so the filtered version, this g0 times this first part, so h0 x of z plus you can actually simply go through that. You can get it. So for the first part, so we have this y0 simply written in the form of y over 2g0 times the x h0x plus h0 minus z x minus z, so time reverse of that. And we have for the y of z, y1 of z, the same thing for the next branch. And the time reverse of that. But here, this should be summed up. So y of z is actually y0 plus y1. When you sum up these and you simplify based on the factors of x of z, the signal factor, then you will get g0 h0. I ignore z, it's much simpler. g1 h1 times the x of z plus something based on x minus z. So whatever here you have as a coefficient of the x of z is something that represents the distortion. Because what you prefer is that x of z to be exactly in the same way in the output. So whatever you have as a coefficient is actually somehow revealing this distortion to the signal. And this part entirely, because you have the time reverse of the signal, this is actually something that makes aliasing. In order to get rid of aliasing, this term should be 0. And in order to have no distortion, this term should be 1. That's the condition of perfect reconstruction. So if we want to have perfect reconstruction, that's the condition, that here we should have 0, this should be 0, and this term, actually the coefficient of xz, should be 1. That's what we're looking for. So in order to have no aliasing, this term is equal to 0, and for no distortion, this term is equal to 1. So it being 1 means that, well, it was 1 over 2 something times the x of z. So 1 over 2, if you just, when you make it equalize it with 1, then 2 goes the other way. And also, you just allow that, because we know that x of n will not be exactly in the same way in the output, so we allow that to be not just 1, but to be z minus l. So it means that l times delay. So we allow that to be l times delay, and this scaling of 2, which was necessary because of derivations. So that's something, if we can satisfy these two conditions at the same time, we have a perfect reconstruction for the filter bank. So I mentioned these two terms again here, but then we'll see that there are different ways to actually get these coefficients. So we can design G and H in such a way that we can satisfy those conditions at the same time. One of the sufficient conditions for having no aliasing is that to choose G0, the synthesis filters, G0 to be like H1 minus Z and G1 as to be minus H0 minus Z. This is one of the selections we can have in order to get the no aliasing filters. And they will see that G0 would be H in time in frequency domain. There will be just a shifted version of H1. So as an example, if you just, can you see that? Is that? So as an example, if you just create a low pass filter H0 having the factors like A0, A1, A2 and so on. So this kind of choosing the filters is actually showing me that G1 should be selected as minus, so the negative of the odd components. Minus A0, A1 is preserved, then minus A2 and so on. And for H1, if we have something like this, then G0 would be like this. So they would be taken, actually, you just derive two of the filters, H0 and H1, and G0 and G1 could be easily actually derived from the analysis filters. Quadrature mirror filter bank is another version of the filter banks that you can easily, by having this kind of selection. So if H1 equals to H0 minus Z, so such that high pass filter is obtained by low pass filter shifting, then this condition will be satisfied and you can have a perfect reconstruction based on that condition. So you can actually ignore aliasing. If you choose G0 in exactly the same way that we have here. So G0 H1 minus C and G1 minus H0 minus C, exactly the same way here. But G0 is actually equal to H0 and G1 equals to minus H1 because of this condition. Because it's mirroring condition. That's a mirroring condition. So that's why this quadrature mirror filter bank, or QMF, is a very efficient filter bank that just by deriving one of the filters, you would be able to actually derive all the other filters. And you have no aliasing. So the no aliasing condition is actually satisfied. But still there are some distortions, and you cannot ignore that distortion unless we have some other conditions actually respected. Yes?
In the example, is there a typo? Is it G H naught of M?
Here you mean?
Yeah. It should be G naught.
Here G naught. Oh, you mean here?
Yeah.
No, you see here? G1 is taken from H naught and G naught is taken from H1. These are reversely taken from each other.
Okay.
That's why it's mentioned like this. So let me go to the next example, maybe it's clear. So for the QMF filter bank, the design of filter bank, so here you have a low pass filter and a high pass filter. But for the QMF, the difference between the QMF and the one that's in general sense two-channel filter bank, the estimated filter bank that we designed in the previous slide actually here, is that for the QMF, just designing H0 would be sufficient and there is no need for any other things to be designed. So you have this H0 and then all the others will be taken based on that. So here you see, here is H0, B0, B1, B2 and B3. So you alternate and flip it. So we have B3 minus B2, B1 and minus B0. This is the H1. And all of the filters are also FIR. There's no IIR filter here. Everything is FIR. So you get H1 here. Then you negate and alternate the signs, you get F1 or the G1 actually here, and the same thing for here, you get the F0 or the G0 actually. So you see, this is called the Smith-Barnwell QMF filter bank. So, but just designing one filter, you get all the information of the other filters. And it respects the no aliasing condition. So you have no aliasing in this type of QMF filter banks. So, and by aliasing, what we mean is that if you have, for example, a low pass filter and a high pass filter like this, then when they are overlapping and they are losing information here, they create some kind of aliasing. But when we say no aliasing, it means that these are as tight as possible to each other, but there is no overlapping. Okay? So this mirror filter bank, as you see, they are mirrors. So the high pass and low pass, they are mirrors. This is the low pass, this is the high pass, and they are mirrors. So the condition for the distortion, not to have any kind of distortion, is that we have to somehow make a kind of power symmetry. And so this is the condition that should be satisfied in order to have the power symmetry and to have no distortion alongside no aliasing that we already got. So that's called the orthogonal filter bank. So orthogonal here is perfect reconstruction filter bank. Another way to choose those coefficients to get actually to those constraints that we extracted for the no aliasing and no distortion. If we choose, so to remove the aliasing, we had this G0 and G0 and G1, so the synthesis filter banks, taken as this, having this relation with G0 with H0 and H1, the analysis filters. If we define P0 as G0 H0, G0 times H0, we know that H0 is low pass filter, and we know that G0 is a low pass filter. Therefore, P0 is nothing but a low pass filter. And if you apply this P0 to the conditions that we have, so we get that G1 H1 is P0 minus C. And if we put these conditions to the no distortion constraint we got already, we get to this equation that P0 minus P0 of minus Z, so the time reverse of that would be just some samples delayed. Then the entire process of doing this and designing this filter bank would be just to go for this P0, design this low pass filter as P0 that satisfies this condition. So we have this condition which only depends on P0. So we try to find the P0 which satisfies this condition, one, and then we try to factorize it to two low pass filters, G0 and H0, and based on that we can easily get the G1 and H1. And this is called the half band filter. And the half band filter is very important because, again, let's go back to the tablet. So the half band filter is very important. So we saw that P0 minus time reversal version of that should be 2. That was the most important equation we had for P0. Yes, yes, sure. For delay you have minus L. Otherwise you're ahead in time. So, so let's have an example. For example, you get a P0 like this: A plus BZ minus 1, CZ minus 2, DZ minus 3, and so on. Then P0 of minus C is equal to A minus BZ minus 1 plus Z minus 2, and so on. So I ignored the rest. This equation means, you know, the first one minus the second one. If you do that, if you apply that, then it becomes 0 plus 2bz minus 1. So these terms actually, these are actually 0. That's the thing that we get in the end. Okay? So it means that if you go for the half band filter, the thing that happens is that I have the freedom to choose just half of these coefficients. So because of this condition that we have here, it actually has no constraint on half of the coefficients. And for half of the coefficients, I have this degree of freedom to choose as I want. So that's the that's called half band filter. So let's actually have another. Maybe it's better to continue here with another color. So, for example, and what is actually giving me is, for example, if you get to this point that P of Z, so this half band filter, equals to this equation. So if you get to this point, so there were two steps that we had to take in order to design the filters based on the half band filter. We were designing, so first we went through the P0 to get the half band filter, and for example we got this. The next step was to factorize this P0 to G0 and H0, but then it gives us the degree of freedom how to choose them. For example, here you can have G0 and H0 with different structures. We can have, for example, here 1 plus Z minus 1, and here the rest of the zeros and poles. So like this. Or you can have, for example, you can have the score of this, and then like this. But different selection of these filters actually gives us different different types of things would be satisfied. For example, for this case, this would be very easy to apply, because here it says that your G0 filter is just a simple low pass filter with having two taps, 1, 1. It's very simple to implement, very fast, very simple. This one, the second one is actually giving me the idea that, so the filters are symmetric, so it means that it has actually linear phase. So we have linear phase shift. While in the first case we don't have linear phase shift. So here we have linear phase shift because it's symmetric. We can have another choice, for example 1 plus z minus 1 square and 2 minus square root of 3 minus z minus 1 and the rest of the terms here. Then it's not a linear phase, but it's orthogonal. It's orthogonal. So different notions come actually out of these different types of selection G0 between G0 and H0. But they are all from the factorization of P0. And you just design the P0 first. Okay? So that was the idea of half band filter. So let's talk about the polyphase structure. So we already saw the noble identity in one of the lectures, that if we can have, so if we have this first structure, so we have a downsampler and a filter, it would be equal to having, I mean, these two permuted. So you can just change their place. If you add m-1 zeros between any of these taps of the filter of JZ. And something quite similar for the upsampling. Now, for this structure of the filter bank that we already saw that, so if we have, for example, a downsampler and a filter, then you can replace their role actually by changing their features like this. And if you have upsampling like this, then you can change their role and their features like this. So it's based on the noble identities. What we extract out of that is the polyphase representation. And what is the polyphase representation? Every filter, so here we have this HZ as a filter. You can easily break it down into the even and odd parts. So if I just break it into two parts with even and odd taps, then they will be represented in the same way. So we have just with Z minus 1 as a factor of the other term, so the second term, for the odd terms actually. Now the polyphase components are defined as this. So for example, E0 is H2n Z minus n, E1 is H2n plus 1 Z minus n, and here you can write it down HZ as E0 plus Z minus 1 E1. So you factorize it into two terms and you get it based on the Z2 with this two terms. In a more specific way, if you have a filter H of n like this is for example H of n and FIR filter, then what does it mean this when I'm talking about the polyphase components? So it means that, assume that this is the filter, then you can write it down based on the superposition of these three types of filters. It's so simple. So we just take, for example, here we have three filters, three sub-filters or three components. So we have to ignore two in between and take the third one actually. Every third sample would be taken for every filter, starting from the first one and then the second one and the third coefficient of that, third multiplication of that, and so on. But then this polyphase component means that You actually take these tabs, but then while writing, you forget about these zeros in between, and just you put them next to each other. The one that's extracted out is the polyphase filter. So if h of n was like this, then the first polyphase component and the second and the third would be like this. You have to just compress this without considering the zeros in between. Then these are the polyphase components. So somehow you're here actually doing the downsampling. So between these two cases, you're doing the downsampling. These E0 or the polyphase components are downsampled version of these components. Okay? And they should be represented like this, which in Z domain is like this. Now in the filter bank, assuming that we are having three tabs, three branches. So we have the first, second, and the third branch. You have sub-bands in three bands. So what we have to do is, in order to have the polyphase structure, what we do is actually the same way that we did here, three different components. So you're actually doing, so that's the filter. The entire thing should be the filter H0 for example, the filter H that we had. So we do this structure, the same as what we have here, written here. But now, if we generalize it for the entire case, now what we can do is, so we had this downsampling coming after the filter. Now the downsampling that comes after the filter, we can take it into the filter, into the block for each of the branches. But then you can replace them. By replacing them using the noble identity, this filter, which was z to the power of d, becomes z. If you have, for example, here d number of the branches, then you replace them, hz z to the power of d just becomes hz. That the downsampler comes to the beginning of the branch. So you just replace the place of them. So the same thing should be happen for the synthesis filter banks. In synthesis part, we have the upsampling. So you do the same thing for the upsampling and filter, and you change the place of them. So by changing the place, what we mean is that the polyphase component of the filter will come to the first part. So for every filter, you just use the polyphase version of that, and upsampler will go to the right-hand side. Here, the polyphase of the H0 goes to the right-hand side, and the downsampler goes to the beginning. And it's so interesting because finally you can actually simplify the entire computation. For example, for the QMF filter bank, we already saw the QMF. So you have these, the G0 and H0 filters. Then for the analysis part, here is what we do. So you have the E0 and E1 components and the downsampler. And for the synthesis part, you have the upsampler and the E1 and E0 components. For the QMF, it looks like this because they have mirror of each other. So E0, E1, E1, and E1 here. And you come up with the polyphase form of that. So the downsampler comes to the first, and then just the polyphase version of that, the same thing for here. You have the mirror of this here, and the mirror of this here, and the upsampler which goes in the end. And that's a more efficient way of implementation, such a way that if you calculate the number of multiplications, here you have d times faster. So d or d minus 1 times faster than the direct implementation. Yes?
The z power minus 1 is considered as a delay, right? So
Delay, yeah.
E1 of z is minus 1 times delayed with respect to E naught of z, right? So that's what this z power minus 1
This tab, actually, this branch is actually having one delay, one sample delay with respect to the first one.
Yeah, okay.
Yeah. The implementation, actually, you don't need actually to go through that in hardware. If you want to implement in the hardware, then this is actually what you need. But in MATLAB, if you want to implement it, it's just simply, doing the math structure, you'll get it. So it's just for your knowledge to say that polyphase implementation is much faster if you are going to the hardware.
Okay, all these things are interesting in the aspect that how do you actually introduce a delay in a hardware sense?
Delay in the hardware.
Like you have an input signal, and then you have this z power minus 1. Okay, so
Every sample, you have every sample as, you have a frequency of sampling. So every sample with respect to the next sample has one sample delay.
Now, how do you introduce that with the hardware?
Now you get an index, an array, and then you skip the index. with
Yeah.
one.
Okay.
So
So
you
you-
get signal as a vector, as an array, no matter what. And then you got it n times, and then you skip every n.
You have one array. Assume that there's a register.
Mm-hmm.
Shift the register for one sample. Then what you get is one sample delayed with respect to the previous one. Okay. Besides QMF filter bank, we also have different other types. Maybe we'd better to skip. The entire lecture 11 and 12 are in the same slides. So they are all in 61 slides that we have to go through. And now we are in slide 33. So in which point we have to make a break and then continue in the afternoon depends on you. We can just make a break right now, or okay. So the rest of the slides would be for the next lecture in the afternoon, which I'm going to finish actually the filter bank and then start a bit about talking about the wavelets, and we have some demos and maybe some trivial MATLAB examples. Thank you.